Hello, everyone. In this session, we're going to talk about loss functions. First of all, where are we now? Where we are now. In the beginning of this class, I gave you this overview. For developing some AI models, we follow these 5 steps. First, we prepare data, both for training and for testing. And after that, we build our models. And of course, we need to use our training data to learn some parameters in our models. That's the third step. And after we train our models, what we do is evaluate our models and to check whether our models show satisfactory performance or not. And in most cases, the first run or first try is not very satisfactory. In that case, we need to improve the performance of our AI models. And to do so, we go back to the previous steps, check whether our data is good enough or large enough, or our model is good enough to tackle the data we have, or are there any problems in the process of training models? And in the process of training models, we first need to define loss functions. That is the topic of this session. And after defining loss functions, we can do something called backpropagation using our loss functions. And then we can optimize our model parameters. So where we are now, we are talking about loss functions for training models. And these are the contents we're going to talk about today. To discuss loss functions, we are going to select one example problem. And using this problem, we're going to discuss our loss functions. And then among various classifiers, we're going to talk about linear classifiers and softmax classifiers. And after we discuss some loss functions, we're going to deep dive into more on loss functions. And then we are going to have a look at regularization and then summarize this lecture. Okay, first example problem. In this session, we are going to select the image classification task as our example problem. This image classification is a core task in computer vision. And what is an image classification task? Given an image containing an entity, there are a set of possible labels. And our goal is to design an algorithm that can choose the correct label among these possible labels. In this case, the image of a cat is given, so the label should be cat. So this is the task of image classification. In summary, the input is an image containing an entity, and the output is one label. However, this image classification task is quite challenging and difficult to solve because, unlike human, computer sees some different things. When we see this picture, we can tell right away that there is a cat. However, in the case of computers see these array of numbers. And it's quite hard to extract semantics from this array of numbers. And an image is a tensor of integers between 1 and 255. Because each pixel is represented with 8 bits, and 8 bits corresponds to 0 to 225, 255. And because we have 3 channels, red, green, and blue, each requiring 8 bits, we need to have, so In this picture, we see just one color, combined RGB. However, for computers, they need to store each number in separate space. Anyway, let's say this image has the height of 800 and the width of 600, and it has depth of 3 because it has 3 channels. And what I want to say is, by receiving these 800 by 600 by 3 numbers, the computers has to figure out the semantics in this image from these numbers. So there is a big semantic gap between what we see from these pictures and what computer sees. And other factors make this image classification task very challenging. The first challenge is viewpoint variation. As we view this object in a different viewpoint, then all pixel values will change. Or as we move our camera, the pixel values change, and it's becoming much harder and more challenging. Another factor is illumination. As you can see here, especially this last picture, if we don't look at this picture closely, then we might not guess that there is a cat. Or just from this picture, it is somewhat vague or ambiguous that this object is actually a cat. Anyway, this illumination is one of the factors that make the image classification task challenging. Another factor is background clutter. As you can see here, this cat blended into this background, and it's quite hard to recognize. And this cat blended into this snow background, and it's quite hard to recognize this part. And another famous factor that makes the image classification task challenging is occlusion. Especially this last picture is very hard to recognize whether this one is cat or a baby tiger. It's quite hard to recognize. Another thing is deformation. Cats show very different poses, and computers have to deal with all these poses without difficulty. However, that's not a fact. And there is also something called intra-class variation. All cats look different, and all objects might look different. Therefore, even though you can recognize one cat perfectly, that doesn't necessarily mean that you can recognize other cats as well, because there are intra-class variation. And context also matters. In this case, this one somewhat looks tiger or something else. Anyway, there are many factors making the image classification task very challenging. And what we want to develop here is an image classifier, and you can view this as designing a function that receives an image, and by analyzing this image in some way, you want to return the class label, the correct class label. However, unlike sorting a list of numbers, there is no obvious way to hard code the algorithm, the image classification algorithm, for recognizing a cat or other classes, because there are numerous numbers and it's quite challenging to develop an algorithm to recognize cats. And when you are developing this function or an algorithm, your algorithm should be robust to all the challenges I mentioned. Illumination variation, viewpoint variation, intra-class variation, occlusion, blah, blah, blah. And there have been some attempts to hardcore code some algorithms to recognize cats. And this, one of the representative approaches was like this. From this cat image, you could extract edges like this. And this one is very famous. And actually this one is called, in fact, called Kenny Edges. And this paper came out in 1986. And until 2000, early 2010, it was quite popular. And using these edges, you could find corners. And some of you who are familiar with conventional computer vision techniques, you might have heard Harry's corners. So corners are different from edges. Edges are like this line or this line. Our corners are the intersection of two edges like this. So here, 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 here. Why do we care about corners? Because corners give more context. And after finding corners, we want to make some hierarchical algorithm to deal with the semantics inside this image. However, they were not that satisfactory. The performance was not very good. And people came up with this idea, machine learning. Rather than hard code our algorithms, what about just using data-driven approaches? In summary, what we want to do is collect a large data set, images and labels. And after that, so example data set looks like this. For airplane, we collect a lot of data, images like this. For automobile, we do the same thing. For birds, cats, deers, we collect a large number of images. We construct the data set. And after that, we use machine learning algorithms to train a classifier. And after that, we evaluate the classifier on new images. Because just memorizing these test image training images doesn't make sense. Because we want to make general image classifiers that can handle the images it never seen. And the flow looks like this. We are designing two functions. The first function receives the training images and the labels for each image. And then we do something called machine learning, which learns the model parameters from these data and construct the model. So that's what we want to do on the first hand. And after we develop this model, what we want to do is predict the labels of these test images and generate the test labels. So this is the data-driven approach. And example data set is CIFAR 10. It contains 10 classes and 50,000 training images and 10,000 testing images. This data set came out in 2009, and it was a very big data set at the time. So, okay, and test images and nearest neighbors look like this. And in the case of frog, the nearest neighbor contains like cats or like airplanes like this. So nearest neighbors is not that, its performance is not that good. As you can see here, this one is airplane, but the nearest neighbor contains birds, horses, cats, or dogs, other entities. So even though this was one of the very first data sets, big data sets, relatively big data sets, but the performance was not that satisfactory. And the thing is, each image has the size of 32 by 32 by 3. Nowadays, icons have better resolution than this. So researchers made a big progress since then. Even though this was a very small image data set, the image size was very small, but it contained like 60,000 images. It was I told you, as I mentioned, one of the very first data sets, big data sets, and researchers are still using this data set. Okay, up to this point, we discussed the example problem, image classification, and think about which of the following is true for image classification. Stop the video and think about it on your own and move on to the next part. Okay, have you solved this problem? The answer is the first one. I told you that it is a task of extracting semantics from an array of numbers. And hard-coded algorithms did not show satisfactory performance. And after 2012, deep learning emerged, and deep learning consumed a huge amount of data sets and huge computational powers, and realized a very high performance image classification. Okay, that was image classification. And from now on, we're going to talk about linear classifiers. What are linear classifiers? Linear classifiers are like building blocks of neural networks. Later on, we're going to use these linear classifiers to build some of our neural networks. And more specifically, linear classifiers look like this. It is parameterized. And the CIFAR10 images have the size of 32 by 32 by 3. And if we flatten this image and make it into one long vector, then it's going to have 3072 dimension. And we are going to fit this image into our linear classifier, which has parameters W. And after that, this image classifier will generate 10 numbers, giving class scores for each class. And linear classifier looks like this. Just this weight is multiplied by the input X, flattened input X. And because we want to generate 10 numbers representing the class score for each class, the input image X has the dimension of 3072 by 1. And because we want to generate 10 numbers, W should have the dimension of 10 by 3072. And after multiplying these two vectors or matrices, the resulting dimension will become 10 by 1. And optionally, we can add a bias. This is optional. You can put it here or not. And because the parameters have linear relationship with the input image, we call this classifier a linear classifier. Okay, to give you a more concrete image or view on image classifiers, linear image classifiers, I'm going to give you an example with an image with 4 pixels and 3 classes. Let's say input image has these 4 pixels. And what we are going to do is first flatten tensors into a vector. Because this input image has 2 by 2 pixels, after flattening, it's going to have 4 by 1 dimension. And because we have 3 classes, cat, dog, and sheep, our parameters should have the shape of 3 by 4. This 4 corresponds to the dimension of the input vector, and this 3 is the number of output number of or classes. And as I told you, this W should have 3 by 4 matrix, and we can have additional bias. And these 4 numbers get multiplied with the input, and with this bias becomes cat score. And the second set of 4 numbers get multiplied to the input as well and added with another bias and generates the dog score. And the last one, sheep score. And to interpret what we are doing at the moment, let's unflatten what we did. So what I mean by this is, we flatten tensors into a vector like this. So 2D input image became 1D vector. However, we can reverse this process, making this 1D vector into 2D vector back. And we can do the same thing for our parameters here. And what we are actually doing is, similar to this one. So input image has 2 by 2, and the first W is also 2 by 2. And what we are doing is element-wise multiplication. So this one multiply with this value, this one with this value, and this one with this value, and this one with this value. So element-wise multiplication, and then sum all these numbers and add another bias, and then it becomes score for the cat class. And we do the same thing for dog. We perform element-wise multiplication and sum the numbers and add this bias, and this becomes dog score. And do the same thing for sheep. Okay, so after we do this, we generate these 3 numbers. And if we learn very good parameters, W, then these W look like this. For the case of car, it looks like a template of a car. And for the case of horse, the W looks like a template of horse. And as you can see here, this approach is checking whether the input image is how much the input image matches with the horse template. So that's what this linear classifier is checking. So the match between the input image and this template. And if the match score is high, then the image classifier will say, oh, this image is an instance of horse. Otherwise, If it matches with the frog template, then it says, oh, it's an instance of frog. So that's what this linear classifier is learning. And we are going to discuss how we can learn these templates effectively in the optimization class. Anyway, that was visual interpretation. And we can also view this geometrically. Let's say this space is 3072 dimensional spaces, and car instances are located here. And we are learning this template, and this template represents this classification space. And images, after multiplied and evaluated, located here, are classified as cars. And images have positions in this part are classified as deer, and the deer template is this line. An airplane template, this line. And other images are ambiguous. It's quite hard to recognize these images. So, linear classifier is dividing these spaces into deer space or airplane space or car space. That's what these linear classifiers are doing, dividing the 30,072 dimensional space into 10 spaces. Of course, there are hard cases for a linear classifier. Let's say if the class 1 is first and third quadrant, and class 2 is in second and fourth quadrant, it's quite hard to divide these spaces with just one linear space. And L2 norm between 1 and 2 and other space, it's also impossible to divide these two spaces with linear classifiers. And if there are 3 modes, it's also impossible. And in the previous sessions, I mentioned this before. To solve this problem, we need to stack some nonlinear activations for linear classifiers, or we should employ some nonlinear features. Anyway, that is the limitation of linear classifiers. And to choose a good W, the structure of W is fixed. The number of classes times the dimension of the input image. So that was the structure of W. However, how do you choose each numbers in this structure? To do so, we need to define a loss function. And this loss function quantifies our unhappiness with the scores across the training data. In other words, how we are not satisfied with current W values. That is what loss function quantifies. And after that, if you are not satisfied, we need to, in some way, change the values of current W and then find the best set of numbers that attains the best performance. That is called optimization. And today, in this session, we're going to talk about loss functions, how we quantify our unhappiness regarding the current values of W. And in the next section, we're going to talk about how we can use these loss functions to find the best values of W. I'm going to give you a simple example to let you understand how loss functions are working. Suppose we have 3 training examples and there are only 3 classes. So the first class is cat, the second class is automobile, And the third class is frog. And what we want to do is calculate the scores by multiplying or matrices multiplication of the input vector and the parameters W. Now let's suppose that for the first example, our linear classifier generated 3 scores as follows. For cat, 3.2, for car, 5.1, and for frog, minus 1.7. And the loss function tells us how good our current classifier is, how good the current values of W. And given a data set of examples, let's say we have n images or n examples. Here, xi corresponds to the input image, and y sub I is the integer labels. So in this example, here, this is the x1, x2, and x3. And y1 could be 1, y2 is going to be 2, y3 is going to be 3. And loss over the data set is the average of loss over examples. So here, we feed our input data, xi, to our classifier f, and this classifier contains parameters w. And this will generate some numbers representing the predicted labels. And we're going to, let's denote the predicted label as y sub I hat. And we, in some way, compare this predictive value and the ground truth value and evaluate the loss for the ith example, because I goes from 1 to n. And after we sum up all these losses, we are going to take 1 over n to calculate the average. That is going to be our final loss. And what is the goal of optimizing this loss function? Calculating the average loss over all data examples. We want to make the model output similar to the target, meaning that the ground truth label yi. So we want to make the model output yi hat and yi similar. And if our prediction yi hat and target yi, if these two values have long distance, then there are going to be large cost or large loss. Cost and loss mean the same thing. And if yi hat and yi have small distance, meaning we have small cost or small loss. And our goal is through our loss functions, we want to make this distance short. And another view is, I told you that our linear classifiers or image classification models predict the scores for each class like this. And we can interpret this one as a probability distribution. And what we want to do here is, let's say this is the predicted probability distribution. And this one is ground truth probability distribution. And in the beginning of training stage, the distance between these two probability distributions might be quite long. And after we train through our loss function, we want to shorten the distance between the predicted probability distribution and ground truth probability distribution. That's what we want to do. And here, KL divergence is one of the metrics that measures the distance between two probability distributions. More details in the following slides. Anyway, we somehow need to be able to quantify a loss. And one of the most famous losses we could use for image classification is multi-class SVM loss. Given an example, xi and yi. Xi is the image and yi is the label. And let's say w dot xi generates scores. And the SVM loss has this form. So in this example, we compare the score of the ground truth label with other class scores. And if the score of the ground truth class is larger than other classes by margin 1, then there is going to be no loss. However, if this is not the case, loss is generated like this. So here, as you can see here, the summation is over all j's, not including the ground truth yi. So in this example, we are going to compare this. In this case, the ground truth is cat, and this one, the ground truth is car, this one, frog. And we're going to compare the score of cat with other scores. And in the case of car, we are going to compare this score with other class scores. This one like this. And if the margin 1 is satisfied, meaning if this score 3.2 is larger than 5.1 plus 1, then there is going to be no loss. However, that is not the case here. And therefore, there are going to be some loss. And this is the first comparison. And in the second comparison, because we need to summate over all j, not including the ground truth class score itself. So we're comparing this score with this one and this one. We need to make two comparisons. And in the first case, loss occurred. And in the second case, for the first example, first training data, when we add the margin 1 here, it becomes minus 0.07. And 3.2 is larger than minus 0.7. And in the second comparison, no loss occurs. Okay, that's how we calculate SVM loss, multi-class SVM loss. And so we are calculating the difference in scores between correct and incorrect classes. And if this difference is larger than 1, no loss occurs. Otherwise, loss occurs linearly, like this. And we can shorthand, abbreviate this expression as this one, max this. All right, the SVM loss has this form. And now, stop this video and bring your pen and paper and calculate the SVM loss for all these three training examples. Training example I equals 1, I equals 2, I equals 3. So calculate the SVM loss on your own and then move on to the next part. Okay, please do it your own because that helps you understand this SVM loss. All right, have you finished calculating the SVM loss? Let's check your calculation together. As I told you, you need to compare this score with that of car, and that of frog. And we need to add +1 because they are the margins. And this one becomes 5.1 plus 1 becomes 6.1. And the gap between these two numbers are going to be our loss, 2.9. And in this case, because 3.2 is larger than this one, no loss occurs like this. Therefore, the total loss for training example 1 becomes 2.9. In the second case, the second training example, we need to compare this ground truth score with cat and frog. And when we add margin 1 here, 4.9 is larger than 2.3 and 2.1, and no loss occurs here. And in the third case, we need to compare minus 3.1 with 2.5 plus 1, 2.2 plus 1, and the gap between these two numbers and these two numbers becomes the loss. And after that, we're going to add all these three numbers and take the average. That is going to be our final loss. All right, that was multi-class SVM loss. And here are some questions I want to give you to deepen your understanding of the SVM loss. What happens to loss if car scores decreases by 0.9 for this training example? So it was originally 4.9, but what happens if it becomes 4.4? And the second question is, what is the minimum and maximum possible SVM loss? Think about it. And the third question is, at initialization, let's assume that W is so small and most scores are predicted as 0. In that case, what is the loss going to be? Express the loss, assuming that there are n examples and c classes. Stop this video and think about these three examples on your own, and then move on to the next part. All right, have you solved all these three problems on your own? Let's check the answers together. The first question, even though our linear classifier produced the score 4.4 for the car class, because this value is larger than 1.3 plus 1, which is margin, and 2.0 plus 1, larger than these two values, loss C is still 0. So there is going to be no change. And the second question is, what is the minimum and maximum possible SVM loss? The minimum value is 0, because here we have 0 here. Therefore, even though this value becomes minus infinity, the minimum value it could take is 0. And the maximum possible value is, of course, infinite. This could be 0 or something else, and this could be infinite. And the gap between these two scores could be infinite. And for the third question, at initialization, W is small, so all scores are 0, 0, 0, 0. And the gap between these two numbers after adding the margin is going to be 1, 1. So there are going to be C minus 1 loss, and we have n examples. So n times C minus 1 is going to be our loss. Okay, so let me elaborate this in more detail. So let's say the first class, second class, third class, fourth class, fifth class, and the sixth class. And every class has the score of 0. Because at the initial stage, W has very small values, and all the scores are predicted 0. That's our assumption. Then let's say the ground truth class is 2, and we need to calculate the loss using this equation. And to do so, we need to add margins to other classes like this. And the difference between these two numbers is 1. And these two numbers is 1. These two numbers is also 1. These two numbers is also 1. So how many ones do we have? Except this ground truth label, we have C minus 1, 1. And this is for one example. And for n examples, we need to multiply n. So we have n times C minus 1 loss. All right, let's move on. And the fourth question is, what if the sum was over all classes? Here we are excluding the ground truth yi. Well, what if we include just this one as well? What happens? Yeah, it's just adding 1, meaningless adding 1, meaningless 1. Okay? And the fifth question is, what if we used mean instead of sum? Are there going to be many differences? It's just rescaling. We're just adding n by 1, n over 1 over n, or c minus 1 like that. That's just rescaling. We could adjust learning rate and reverse this rescaling. So it's not much difference. The sixth question is, what if we use squared version rather than just this number? Then the behavior is totally different because this one is called squared hinge loss, not just SVM loss. And it has totally different behavior. So rather than linear behavior here, it has quadratic behavior. All right, that was about SVM loss. And now let's implement SVM loss together. Implementing SVM loss is quite straightforward. We're given the input image, the label, and our weight, W. And we first need to calculate the scores, and we are going to calculate the dot product between W and X. And we need to calculate margins. We're going to use the same equation as the SVM loss. From the calculated scores, we're going to subtract the ground truth score and add 1. And the ground truth label should not have any value, so we're injecting 0 here. And the loss is by summing all these numbers in this margins vector, and we just return loss 5. That's all about SVM loss. Pretty easy to implement.